I want to address this question, and it will be interesting to hear at the end of my talk whether I've actually convinced you that climate change is a defining challenge for the 21st century. But I thought I'd actually start with a bit of history, because we kind of sort of think that climate change and the notion of human-induced climate change is something that's really built up in the last few decades, but actually it goes back quite a bit further. And Svante Arrhenius, who was a Nobel Prize-winning physicist, had worked out that actually if you increase the carbon dioxide concentration in the atmosphere, the Earth's going to warm. And he built this idea up based on John Tyndall's experiments earlier in the 19th century. And John Tyndall had shown that the Earth must have a greenhouse effect for it to have the temperature that it does. Without it, we would be freezing cold. And that he showed that certain gases acted both to absorb and emit long-wave infrared radiation. And those gases, of which the dominant greenhouse gas, water vapor, is why we have the equable climate that we do. But of course, he also identified carbon dioxide. And it's interesting that way back over 100 years ago, in a book called Worlds in the Making, could have been written today, couldn't it? He wrote, "The enormous combustion of coal by our industrial establishments suffices to increase the percentage of carbon dioxide in the air to a perceptible degree. Any doubling of the percentage of carbon dioxide in the air would raise the temperature of the Earth's surface by 4 degrees C, and if it were increased fourfold, the temperature would rise by 8 degrees C. So here we are, some very basic physics, and he wasn't far off the mark, because if we look now at the most recent assessments done by the Intergovernmental Panel on Climate Change, we think that the sensitivity of the planet to a doubling of CO2 is between 1.5 and 4.5 degrees. In fact, we're beginning to think it's not as low as 1.5, it's probably 2 to something like 4.5. So actually, the physics has been there for a very long time. But of course, Arrhenius didn't really know many of the things that we know today, and he went on to write something along these lines: by the influence of the increasing percentage of carbonic acid in the atmosphere, we may hope to enjoy ages with more equable and better climates, especially as regards the colder regions of the Earth. Ages when the Earth will bring forth much more abundant crops than at present for the benefit of rapidly propagating mankind." So he'd anticipated population growth. He'd also thought rather simplistically that if we all get a bit warmer, actually this is going to be quite a nice planet to live on. I have to say that with all the scientific research that we've done since then and all the evidence we've gathered, it's hard to be as optimistic as Arrhenius was over 100 years ago. So what I want to do in this lecture is just take you through some of what we've learned almost really in my career as a scientist, where we've arrived at today, and have a little bit of a look into the future. There'll be a little bit of science, but I hope much more sort of trying to think about climate change as a part of the whole global system in which we live. But I wanted to start by just taking those two words, climate and change, because we often just assume when we talk about it that people know what we mean by climate, and they know what we mean by change. So what is climate? Well, it's, in its simplest terms, it's the long-term average over some period, to be defined, of the weather that we experienced day by day, season by season. This is an example of the annual mean rainfall for England and Wales going back to 1760. And you can see, first of all, that on average, over those hundreds of years, our rainfall has not changed very much, but actually it's quite volatile from year to year. So we live, and we all know that, we're quite used to the fact that our weather is highly variable, and we've adjusted to that. And so we can take that long-term average and say, yes, we understand what our climate is. We have to think about what that long-term average means when we talk about change. And just to say, of course, that in some parts of the world, of course, a stable climate is really, really important. We are used to this rather volatile climate, but in places like India, the economy and the livelihoods of the population, food security, water security, have become very finely tuned to a very stable, reliable climate. The monsoon in India arrives every year on the 1st of June, roughly, in southern India. It sweeps in a very well-defined way across the country that you can map by dates. We couldn't possibly do that in this country, could we? And a late arrival of the monsoon has quite severe economic and social impacts in terms of water resources and farming and so forth. So there's an example where you've got a very, very stable climate, and the rainfall of the Indian summer monsoon varies less than plus or minus 10% from year to year. So a really big change in the monsoon would be absolutely devastating for India. So what about change? Well, here's another bit of our climate, and this is temperature in this particular instance. And what we can see here is that there is a change going on. And if you talk about change, you have to talk about, well, what's the norm? And I think that's been quite difficult. Some people think that the norm is what we had last winter, or next winter, or the previous winter. So when we have a cold winter, like this last year, then people tend to say, oh, well, climate change, ha ha. Nothing's going on, is it? But we have to define the period over which we're deciding that change is appearing. In this particular example here of temperature, we can see that the UK has warmed up in the last couple of decades to a degree that it's now warmer than anything we can really see over 200 or 300 years, bearing in mind the uncertainty in the observations. But I think that the best way to think about change is change in relation to what we as a society are used to dealing with. And therefore, from the perspective of the IPCC and from the scientific perspective as well, we tend to think of change with respect to a norm that, say, covers the last 30 to 50 years, or maybe 100 years. It's the margins that we as a modern civilization have experienced and adjusted to. A modern civilization which is globally interconnected with the population that now exists on this planet. It's not the same as, say, looking at the climate over 100 years ago. The issues that we have to deal with are quite different. So that's how we define change. But then people say, well, okay, that's all very well, but the climate has always changed, so why should we be looking at this particular change that we're seeing now and saying that it's anything different going on? So this is a very iconic figure, I think, from the ice cores from Antarctica, mapping 800,000 years of climate. And in the top graph in red, you can see the carbon dioxide concentration inferred from those gas bubbles in parts per million by volume. And what you can see is that it ranges between just under 200 to just under 300 parts per million by volume. We can also see these regular, almost like a heartbeat of the planet, of these ice ages coming and going, the glacial interglacial cycles. And as the carbon dioxide goes up and down, we can see on the lower graph in black Temperature, in this case, it's actually using a proxy which is to do with deuterium, but in fact, the extremes of the temperature perturbations that we can see are roughly about 9 degrees, 8 or 9 degrees between a full glacial and an interglacial, just to give you an idea of the scale. So it's an important number to remember, 8 degrees. And we can see this heartbeat of the planet, and you can say, well, okay, so why is today any different? Why should we be worried? The planet's always been going in and out of glacial interglacials. Our climate has always been changing. The first thing to say that it's about the source of the change. When we look at this in much more detail, we can see that actually the temperature changes before the carbon dioxide changes. So what is happening here is that the changes in the orbit of the Earth around the Sun and the tilt of the Earth means that the main forcing is how much solar energy, how much heat the planet gets from the Sun. As the temperature changes, the biosphere adjusts and either shuts down or increases its emissions of carbon dioxide. So here we see already that the physical climate system, the temperature, is very closely linked to the biosphere, and we'll come back to that later on. The key point here is that temperature leads carbon dioxide, whereas when we look at what's happening today, the carbon dioxide is rising first, just as Arrhenius thought it would, and the temperature of the planet is responding. So they're different drivers. And therefore, although we can learn from the past, they're not analogues of what's happening today. The other thing that marks out what's happening today is the rapidity of the change. So I've put a little red star on there. That is actually where we are today in our CO2 concentrations. We are now over 400 parts per million by volume. We are well above anything that this planet has experienced in the last 800,000 years. And you have to go way back into the very deep past to find situations where the planet had much more carbon dioxide than today, and of course was much warmer. And this really began to come to the fore, actually, in the early 60s. This is Charles David Keeling, and this is the carbon dioxide curve at Mauna Loa Observatory in Hawaii, often known as the Keeling curve. And he started really just out of sort of interest, really, measuring carbon dioxide in the late 50s. And in the early 60s, he noticed that, well, first of all, it was already over 300. He noticed that it was rising inexorably year by year. The little red line that you can see there is actually the seasonal cycle in the carbon dioxide, and this is the Earth's biosphere breathing in and out. Because the northern hemisphere has much more land than the southern hemisphere, we can see the breathing in and out of the northern hemisphere biosphere. That's what's going on if you're interested in that. And here we are, this is the latest graph for June, and we are now well above 400. In fact, we're approaching 410. I started my career in the Met Office in the early 70s, and by then it was just above 320. I wrote the early radiation codes, and I remember coding in 320 as the concentration of the carbon dioxide. And I remember writing a paper in the mid-70s on the effects of a 2 times CO2 world on things like humidity and clouds and so forth. It was published in a book, actually, called Carbon Dioxide, Climate and Society. But I have to say, in the mid-70s, I thought this was really quite an interesting scientific problem. I had no idea that it would become, by the end of my career, one of the major global issues. Perhaps I just didn't see it, but, you know, we were just along the flattish part of that curve. So it's the second thing that marks it out is that it's rapidly, our atmosphere is rapidly changing. The CO2 concentrations are rising very, very fast indeed, and our climate is changing at a rate that is probably an order of magnitude faster than anything we've can detect from looking at glacial interglacial cycles. And we know that what's happening, why we're seeing those concentrations rise in the way that they do, is because we're burning ancient fossil fuels. We're releasing carbon that was locked up in the deep earth over millennia and releasing them in a very rapid, in just a few decades. And so this is just showing the contributions over time of the different components of the carbon emissions. And land use change, of course, has been very important in this, and we shouldn't neglect that, because actually before about 1950, land use change was the dominant source of CO2. And it continues to be a significant source. Where does all that carbon go? Well, actually, this comes back now to the role of the biosphere. We know that around about half of what we emit is taken up by the land and ocean biospheres, and only about a half remains in the atmosphere. So we're fortunate in the sense that the biosphere is buffering us from the worst effects of our emissions. But the question is, how long will it continue to do so? And will in the future it be more efficient or less efficient in helping us deal with our CO2 emissions? So the pace of change for the planet is extraordinary, and we can see that in the way that ecosystems are unable to adapt. We can see that in the increasing extinction rate of species. We've cut many of the feedback loops with this rapid release of carbon dioxide that in the past has allowed the Earth as a living organism to adjust to climate change. And the final thing, of course, that makes it so different from anything in the past is the scale of the human enterprise in what I've called a globally interdependent world. And this figure really, I often call this the circle of securities, because the white circles around the outside are the securities that we as a society rely on for our health and well-being. And you can't look at any one of them separately from the other. They're all interlinked. We can't look at food security without looking at water security. We can't look at energy security without thinking about health and political security and so forth. So those are what we rely on in this very globally interdependent world. But in the middle are what I think are the key drivers of 21st century change. And this is important because we can't look at climate change in isolation from other things that are happening in the world that will challenge us in the coming decades. We've got urbanization, the growth of megacities, often on coastlines, with more and more of the world's population living in cities rather than in the countryside. We've got population growth. The Earth's population now is, I think, around 7 billion and continuing to grow. And the pressures on ecosystems and on the whole infrastructure of society is very difficult. And we've got limited natural resources, of which I think water will become the most precious resource. And then we have on top of that weather, climate variability and change. And you'll see that I haven't just said climate change, because actually even today, and climate change has yet to bite seriously, we are very exposed and vulnerable to extreme weather and to the variability of our climate, the natural variability of our climate. So we need to think about not just climate change, but what's our weather going to do from day to day and from year to year. And actually, Sir John Beddington, when he was government chief scientist, called this the perfect storm. He said, can 9 billion people be fed equitably, healthily and sustainably? Can we cope with the future demands on water? Can we provide enough energy to supply the growing population coming out of poverty? And can we do all this whilst mitigating and adapting to climate change? So this is the challenge. This is what we're here to talk about tonight. Since I started my scientific career, there has been a huge transformation of our science. And it begins with observing the planet. All good science starts with observations. You have to understand to know the system that you're looking at. And when I entered the Met Office in the early 70s, we were just at the very beginning of the satellite era. I can still really just remember the first satellite images coming in showing us how clouds were organized and things like that. Things that we had just no idea about, which we take for granted today. But today, of course, we have this huge myriad of satellite instruments measuring all sorts of things about our planet. We have in situ observations from planes, from ships, from buoys, from radiosondes, and increasingly from autonomous vehicles within the ocean. So we know a huge amount about our atmosphere, how the weather is evolving, how the ocean is changing, and so forth, that we didn't know even 20 years ago. And from this, we've learnt about the flows of energy through the global system, and we've been able to detect that the Earth is gaining energy round about 0.9 watts per metre squared is the imbalance now at the Earth's surface, and most of that additional heat is being taken up by the ocean. All these things we've learnt in the last 20, 30 years from Earth observation. And of course, it's allowed us to detect that our climate is changing in all sorts of ways. We're quite used to hearing about global mean surface temperature and 2 degrees or whatever. But it's only one metric of a changing climate. And this is a figure from the IPCC report, the last one they did, the 5th assessment report in 2013. And we can see the signature of climate change in many things: sea ice area, glaciers, snow cover, sea level rise, ocean heat content, temperature over land, and so forth. And I'm not going to spend any more time on that because it's quite familiar to many of you, I'm sure. But it's fair to say that observations tell us an immense amount about our climate and how it is changing, but not necessarily how the climate system works and why it is changing. And so the other great revolution in my career as a scientist has been the building of these things called climate models. And this was just beginning, really, when I started in the Met Office in the early 1970s, and I was involved in building some of the first climate models. And it's very important, I think, when we talk about climate change, is to explain what a climate model is, because everything about climate change depends really about understanding what these models are. And there's a great myth out there that they're somehow empirical models, like an economic model and many other models, where you're basically just looking at observations, producing empirical relationships through some very sophisticated statistics and using those to infer things about the present and the future. Climate models are not like that. They're actually really simulators. They're based on the fundamental laws of physics, which we then solve by cutting the Earth's atmosphere and oceans up into these volumes, millions of volumes, in fact, and watching how the physics tells us how the atmosphere and oceans will evolve. And I'll say a bit more about that in a minute. But these climate models are absolutely fundamental in many ways to our understanding of climate change and what it might mean, because they help us to explain how the climate system works. They help us to understand why it is changing, and they allow us to look into the future and see what our climate might be like depending on what we decide to do with our emissions. So I just want to spend a few minutes just telling you what's in these climate models, some very basic physics. And my apologies to those who are physicists and know all this stuff. But anyway, there we go. So we're going to go back to basics and some classical physics. And I should say that actually the models that make the weather forecast every day are the same codes that we use fundamentally in the climate models. But the first one is Newton's second law of motion. Force equals mass times acceleration. I think we all remember that one. What's really much more interesting than that equation suggests is, of course, that we actually live on a revolving sphere. And so there's something called the Coriolis force that comes into play, which is what makes our circulation of the planet so interesting. And indeed, the sort of weather that we experience, particularly in our neck of the woods here, is very much determined by that rate of rotation of the planet. And the sort of big waves in the jet stream that we observe comes quite simply from force equals mass times acceleration in the presence of the Coriolis force. We have something called the hydrostatic approximation. That basically tells you how pressure decreases with height. So you're balancing the pressure gradient force with the pull of gravity. In the most sophisticated models today, we don't actually use the hydrostatic approximation anymore because in some systems, like big thunderstorms and hurricanes and so forth, that balance doesn't exist instantaneously. But in the climate models, largely we still use that approximation. The mass continuity equation, what goes up has to come in at the bottom to fill the space that's left behind, quite simply. Relates vertical motions to the convergence of the wind. The ideal gas equation, PV equals RT, relates temperature with density, warm air rises. In fact, I was quite interested reading about Robert Hooke the other day to actually realize that he was deeply involved in the earlier version of this before we got to temperature, which was Boyle's law, that pressure and volume are inversely related. Then we've got the first law of thermodynamics that links heating to changes in the winds. So heat is work and work is heat. And the biggest term in that actually is the latent heat release from clouds and rain, snow, precipitation as that forms. And they dominate the Earth's heat engine. And what makes our climate on this planet so absolutely fascinating is that water can exist in all three phases within our climate system, as a solid, as a liquid, and as a vapor. And that ability to move heat around the system in terms of whether water's a vapor or a liquid or a solid makes our weather endlessly fascinating and actually endlessly difficult for us to simulate in our climate models. But that's another lecture. There's something called the Clausius-Clapeyron equation, which some of you may have heard of if you did moist thermodynamics as a physicist, and that relates saturated water vapor pressure to temperature. And basically what it says is that warmer air holds more moisture. And you often hear that quoted to explain why a warming world we're going to get much heavier rainfall. That's the basis there. And then we've got Planck and Stefan Boltzmann's laws that link thermal radiation emitted by a black body, and a black body, in this case the Earth's surface is pretty much a black body, and most clouds are, apart from ice clouds, are black bodies. So that's a very simple relationship. And then we've got Kirchhoff's laws, which link absorption and emission of radiation by atmospheric gases. And that's actually a very critical part of explaining the greenhouse effect. That greenhouse gases, water vapor, carbon dioxide, ozone, are both absorbers and then emitters. So they can absorb the infrared radiation coming out of the Earth's surface, and then re-emit at the temperature at which where the gas is sitting in the atmosphere, which is usually colder than the Earth's surface. And that's how we trap heat into the climate system. So that's basically it. And you may say, well, okay, so why all this uncertainty? And it's true that when I started out in climate modelling, and this is what we had, we got about 75% of the answer right, I would say. We were able to simulate the poleward transport of heat by the atmosphere in the oceans to quite an accurate level. But when you get down to the more regional and local detail, then what starts to matter are things that are below the resolution or the grid of the model. Things like clouds, things like rainfall, those sorts of things, the effects of the landscape on the flow. And so we've spent probably the last 40 years trying to work out the best ways to represent what we call those sub-grid scale processes, how best to represent those in our models so that we can tell you whether it's going to rain over your town tomorrow and so forth. And we still haven't really reached the end of the road on that. And that's where a lot of the uncertainty in the future projections on climate change come from, things that are happening on the very fine scales, like rainfall, like clouds. But there we are, just basic physics. And we take those and we integrate them forward in time. We simulate the flow of air and water, the winds in the atmosphere, the currents in the ocean, the exchange of heat, sensible and latent, so that's heat and evaporation and momentum between the atmosphere and the Earth's surface, the release of latent heat by condensation during the formation of clouds and raindrops, and the absorption of solar radiation and emission of thermal infrared radiation by clouds, the atmosphere, and the Earth's surface. And what you get is a simulation of the three-dimensional evolution over years to centuries of the world's weather and climate. And it looks something like this. So this is a model simulation of, in this case, clouds represented using the infrared, as if you were looking down on the Earth in the infrared channel, where the white clouds are the high clouds, the grey clouds are much lower. And what you can see in this, you can see that the sun is going round. So we have the diurnal cycle. You can see the sun coming past on some of the tropical land masses. You can see the fronts in both the southern and northern hemisphere in the what we call the storm tracks. You can see the tropical clouds building up as the sun goes past the diurnal cycle. We can see tropical cyclones. Now, if you're a convection cloud expert in the tropics like me, I can tell you that that's not very good. This is with a grid of the model of 12 kilometers. So this is pretty much where we are at global weather forecasting today. This is actually a climate simulation. But what I want to get across to you, that this is not an empirical model. This is actually a simulation from first principles, where the fundamental constraints are really just what's the solar constant, what's the rotation rate of the planet, what's the geography of the planet, where are the land masses and the mountains, and not even we don't even tell the atmosphere what it's made of, because the physics produces the water vapor that makes up the atmosphere. And increasingly now, we don't even tell the model how much carbon dioxide there is in the atmosphere. We give it the model the emissions, and the chemistry goes away and works out what the carbon loading of the atmosphere is. So these are really quite remarkable things. And we can go back, actually, and this again goes back to my very first days in this subject, the very famous paper by Manabe and Weatherald, and this is back in 1974, and this is why I say we had 75% of the answer, even from just the basic physics. And he, in this iconic paper, again, said, well, the global warming for a 2 times CO2 world, see, he's very accurate, 2.93 degrees. So he was bang in the middle of where we think it is today. But he also identified some other things that we hadn't observed at that point, particularly stratospheric cooling. And that is actually, for me, the killer fingerprint of a CO2-induced climate change. You cannot explain why the surface warms and the stratosphere cools if you say it's due to the sun or to any other factor. CO2, through the nature of the way that it works as a greenhouse gas, is the only way in which you can get warming at the surface and cooling in the stratosphere. So that cooling, which he predicted and which we now observe, is for me the killer signal, the fingerprint of CO2-induced global warming. So there we are, even in 1974, very basic climate model, very basic physics, telling us pretty much all the things that we now observe. But actually, what we also need, of course, and why the other part of the big story on climate change is supercomputing power. And these are just a few of the supercomputers that I've worked on in my career. We pretty much followed in climate science Moore's law, which tells you that the power increases doubles every 18 months. Thank you very much. I knew there'd be somebody who knew exactly what Moore's law was. But anyway, the progress of our understanding of climate change is intimately related to the increase in supercomputing power. And this is the Cray at NCAR, where I was in the 1980s. We worked, a team from the UK worked on the Earth simulator. This is the IBM at the Met Office, and then this is the latest Cray that I was part of the team that procured that about 2 or 3 years ago at a cost of nearly £100 million. So this is not for the faint-hearted. And it's a 13 petaflop machine, peta being 10 to the 15, or 1,000 million, or something like that. It's a big beast, and it needs to be a big beast because it's got to do some very big stuff. And here's an example of what you get when you have the power to increase the number of grid cells in your model. This comes at a huge cost. When you halve the resolution, you need an order of magnitude more power. Is roughly how it goes. So this is a picture of a simulation of the ocean surface currents, and white are where the currents are moving more quickly. And we can see on the far side there what the ocean model looked like that was used in the 5th assessment report of the IPCC. And it's very fuzzy. The ocean is hugely under-resolved. And when we think about the fact that the ocean takes up 90% of the heat associated with global warming, then our inability to represent major ocean currents, the upwelling zones and so forth, the way in which the ocean, the processes through which the ocean takes up heat, then we have an uncertainty there. And we can see that as we go now to the 20-kilometre grid for the ocean, which is what's going now into the 6th assessment report, all of a sudden we start to see some real structure. We start to be able to pick out the important ocean eddies. We can see here the lovely Agulhas rings being shed off the tip of South Africa here. We can see this boundary current running down here. We can see some other currents through Gibraltar, and we can see the structure in our Gulf Stream, and we can see some very interesting boundary currents here around the coast of Norway and so forth. But still, the eddies are under-resolved, and now our experimental system is running at 5 kilometres, and here's an example, and we can see all these instability waves around the cold tongue in the equatorial East Pacific, which we postulated a decade or so ago were an important part of the heat budget of this region where El Niño forms. And indeed, we get a much, much better simulation of El Niño and of that cold tongue. We can see here this current and these whirls that develop in the Gulf of Mexico, and here's the Gulf Stream, the currents associated with the Gulf Stream being shed off Cape Hatteras. It's only when you get down to that sort of level of resolution that you begin to capture the detail that's there in the real world. The code is exactly the same. So the physics hasn't changed. It's our ability to be able to solve those physics equations through the use of computer power. The other thing we've done, of course, is to actually add a lot more components to the simulation. And now we call them Earth system models. And they include the terrestrial carbon cycle. They include things about the atmospheric composition. And they include information about the sea ice and glaciers and the plankton and biology of the oceans. So they are essentially becoming simulators of the whole Earth system. And the next big step, of course, is to put humans into it. And that is yet another lecture. But people are thinking about how do you put humans as agents within the Earth system. Fascinating. But look what you can do. This is actually a rather nice movie from the group at Max Planck Institute in Hamburg. And this case is looking at the phytoplankton as a function of time, and we can, through the seasonal cycle, and we can see the phytoplankton blooms occurring in the northern seas, and then as we come south, we can see the massive bloom in the Antarctic seas during the summer, which are the biggest blooms on the planet. We can see that a lot of the biological production is going on in eddies and on fronts in the ocean where you've got lots of eddy mixing and upwelling of nutrients. This is a model simulation. It's using the physical simulation of the ocean currents and eddies, working with an ecological model to tell us what the phytoplankton concentrations are in the ocean. And this is the sort of thing that we can see here on the cold tongue here across the Pacific and the instability waves that I talked about. This is the sort of thing that increasingly we have to be able to do if we're going to look at the full ramifications of climate change and the impact on ocean biology, as well as what happens to us on land. So these are remarkable codes, and they run typically, in the Met Office code, ran to nearly 2 million lines of code. These are huge endeavors. And actually, I think this is one of the great unsung successes of science in the last 50 years, our ability to be able to simulate and therefore to be able to interrogate this very complex system that we can't do through observations, and to use it to say, what does the future mean? So, I'm a scientist, and this, as a climate scientist, I can't go and do experiments on the real world, except perhaps the grand experiment that we've done by emitting lots and lots of carbon dioxide, which has been pretty interesting. But to a large extent, the models are our laboratories, along with a supercomputer, which is why I've been fighting a lot of my career for both better models and bigger supercomputers. Because actually they're not just for making forecasts. Climate models can be used to test hypotheses about how the climate system varies and changes. We've used models to understand what effect the mountains have on our climate system and things like that. We can use them to understand climate responses to forcing agents, such as greenhouse gases, but also volcanic eruptions, solar variability, and so on. And we can use them in clever ways to pick apart feedbacks and interactions within the climate system. So if I change something here, what's its global influence? Can I understand how El Niño affects the weather in the UK? And we can perform what I call what-if experiments. And this is probably the most important what-if experiment that we've done with climate models. And this is to ask the question of what would the world have been like, what would our climate have been like if we hadn't emitted greenhouse gases? And we can do that by taking the model and running it without increasing greenhouse gases for the 20th century. And this is an example of that. It's not for global mean temperature, it's actually for European summer temperatures, something that's much closer to home and that we can relate to, particularly after the 2003 heat wave and subsequent rather hot summers. And what we've done, and this is pretty typical, is that you don't run the simulation just once. Because as you saw at the very beginning of the lecture, the climate is naturally very volatile. The climate's a chaotic system. It varies hugely from year to year. And as Ed Laurent said, one flap of the seagull's wings forever changes the course of the weather. So you can never run just one simulation. You have to run a whole set, ideally 50, 100, those sort of things. So you can understand the range of possible climates that you could get for a particular forcing. And so here we've got two sets of simulations. We've got the world that is, in red, pink, with greenhouse gas emissions, and the world that would have been without greenhouse gas emissions. And then we've got the black line, which is the observations. And you can see the observations are also very volatile, a lot of year-to-year variability. And for most of the 20th century, the observations lie both within the green and the red range of simulations. But since about 1995 for European summer temperatures, you can see that actually the observations have moved out of the green range. In fact, they're running actually at the higher end of what the models think European summer temperatures should be. And we can see the 2000, I can't really use the pointer, but we can see the 2003 heat wave there and so forth. And what this allows us to say is that the changes that we detect from observations cannot be explained without invoking human emissions of greenhouse gases. And this is the classic attribution statement that underpins the whole of the IPCC. It's these experiments, these what-if experiments, that have convinced the world's governments and politicians that climate change is due to us. And we could not have done that without the climate models. The other things, of course, that climate models allow you to do is to look into the future. How much warmer will it get? And again, we've all seen these diagrams here. But what I wanted to do is, rather than sort of just show you endless pictures of the future in terms of temperature and rainfall, is just to tell you a little story to try and make it real. And so I want you to imagine our climate in 2050. And it's not that far away on this diagram, if we fail to curb our emissions. And if so, it's 2050, we're up on one of these curves, and the Earth's surface temperature has passed 2 degrees for the first time. And global sea level has risen by another 30 centimetres. The Arctic is now ice-free in summer, and there have been substantial increases in its ocean temperatures. In the Arctic, marine mammal, fish and bird populations are changing, and the indigenous population is increasingly compromised by lack of food security, loss of coastal sea ice, sea level rise, and increased weather intensity are forcing relocations of some communities. The opening up of the Arctic has made it a major shipping route for international trade, and exploitation of Arctic's natural resources is growing rapidly. New invasive species brought in by increased human activity are changing natural ecosystems. In India, pre-monsoon heat is now crippling for much of the population. especially across the northern plains. And flooding during the monsoon season is increasingly serious as daily rainfall intensities rise. Those living in low-lying coastal areas are experiencing more and more frequent incursions of seawater during storm surges as sea level rises. Freshwater supplies are contaminated, agricultural land is damaged, and waterborne diseases are increasingly common. Forced migration is increasingly an issue. On the positive side, and let's not forget that, air quality has improved substantially and fewer people are affected by respiratory ailments. Across the tropics, construction and maintenance of infrastructure in major towns and cities has become more difficult as daytime temperatures frequently exceed thresholds where it is safe to work outside. Several small island states, such as Kiribati, are no longer habitable because of sea level rise, with a population now stateless with an uncertain future. In others, coral bleaching has led to the loss of sustainable fisheries on which the population depend for their future, for their food security. Tourism, which was the major part of their economies, has fallen away. Southern Australia and the Mediterranean, including the Middle East, are now in the grip of prolonged droughts and periods of extreme summer heat. Wildfires are becoming increasingly dangerous, threatening homes and urban environments and damaging natural ecosystems. In the UK and Northern Europe, the weather is increasingly volatile, and we have invested more and more on flood defences and learned how to manage our local environment to mitigate some of the adverse effects of climate change. Summer heat waves are becoming more prevalent, and the winter ski season is increasingly unreliable as rising temperatures lead to loss of snow cover. But longer growing seasons and warmer temperatures are providing opportunities for diversification in food production and tourism. So what we can see here, just in that little snapshot, is what our projections are telling us about what the world could be like in 30 years' time. And actually we're seeing signs of this already when we read the news, particularly over the last year, in terms of drought and forest fires and storms. And in all of this, water, I think, will become the Earth's most precious commodity. And we can see already legal, political debates about who owns water when aquifers and rivers cross national boundaries. So water will become something that wars may be fought about in the future. And of course, finally, it's worth saying that climate change will increasingly be about human rights and justice, and this was very much how the discussions at the COPs have gone, and certainly when I was in Paris in 2015, this was becoming very important. And it's just worth saying this quote from the UN: "Climate change affects many human rights, undercutting the rights to health, to food, to water. It may even affect the right to self-determination." I'm going to press on because I know time is running out and it's all in the transcript. But I just wanted to turn to 2015 because this was in many ways a landmark year, not just because of the Paris Agreement, where many countries for the first time stood back and said, actually, we accept the science. What are we going to do about it now? For me, it was a watershed moment. It was the end of the beginning of the fight to deal with climate change. But we also had the Sendai Agreement, which was about substantial reduction in disaster risk and losses in lives, livelihoods and health. And of course, we have the Sustainable Development Goals. And in all of these, understanding and quantifying weather and climate risk are at the core of these actions. If we don't deal with climate change, we cannot fulfill the ambitions of the Sendai Agreement or the Sustainable Development Goals. And if we look at the global risk landscape from the World Economic Forum this year, we can see the green diamonds here are all things to do with climate change and our weather, extreme weather events, natural disasters. Failure of climate change mitigation adaptation is up there as one of the top 3 risks for the World Economic Forum. And if we look at what happened just last year and the huge losses from natural catastrophes, this is the wake-up call. As a society, we're not well equipped to deal with not just what climate change will throw at us, but what the climate today can throw at us. So what can we do about it? Well, you'll be glad that I'm not going to go into this in great depth. We can change how we produce and store energy. We can change how we use energy just by being more efficient. And we must change how and where we live in all sorts of ways. And I wanted to leave the last word, if I may, to a friend of mine, Piers Sellers, who was the first British astronaut, and he flew on the space shuttle on a number of occasions. What some of you may not know is that he was a land surface scientist, and he and I used to interact around the climate modelling arena before he was elevated to become an astronaut, but we remained good friends. And he died of pancreatic cancer in December 2016. And the year before, when he received his diagnosis, he wrote a very moving piece in the New York Times on his perspectives on climate change. He said, "New technologies have a way of bettering our lives in ways we cannot anticipate. There is no convincing demonstrated reason to believe that our evolving future will be worse than our present, assuming careful management of the challenges and risks. History is replete with examples of us humans getting out of tight spots. The winners tend to be realistic, pragmatic, and flexible. The losers were often in denial of the threat." I can vouch for that, actually. More seriously, he then writes, "As an astronaut, I spacewalked 220 miles above the Earth. Floating alongside the International Space Station, I watched hurricanes cartwheel across the ocean. Gigantic nighttime thunderstorms flash and flare for hundreds of miles along the equator. The Amazon snake its way to the sea through a brilliant green carpet of forest. From this God's eye view, I saw how fragile and infinitely precious the Earth is. I'm hopeful for its future." Thank you very much.